Going to give the second lecture on string.
Okay, so today is in the morning I will give an introduction to superstrings, and then in the afternoon we can relax a bit and have some fun and apply all these things to low energy effective interactions and modular graph forms. So, I have to turn this thing on. So yesterday I explained that string theory is really a theory of fluctuating random surfaces governed by a topological expansion in the genus, given schematically like so. But we only looked at the bosonic string, and that string has a tachyon, so it's unphysical and unstable. But more importantly, it has no fermions, and nature does have fermions, for sure. So superstrings generalize the bosonic string with space-time fermions and eliminates the tachyon, and will have space-time supersymmetry. So there are several ways known to introduce fermions into superstring theory. And I've listed them. I have this arrow. I should have thought of that. I have listed the main ones. Whoops, the main ones here. So the oldest one, and probably best understood today, is the Ramon-Schwarz formulation of the fermionic string, supplemented with the GSO projection, which truncates the spectrum to one that is supersymmetric. Then there is the Green-Schwarz formulation, which is space-time supersymmetric, but has been resisted direct quantization for 30-something years. There's a light cone formulation, which dates back from the 70s, and which on the face of it is very useful because there are no negative norm states from the beginning, but in practice has turned out to be quite tricky to quantize. There is string field theory. There are other things like topological string theory. And finally, the Berkovits pure spinor formulation, which is a reworking, a reformulation of the Green-Schwarz formulation that is hard to derive from it, but actually builds in supersymmetry in space-time, and mysteriously has actually been quite successful. So we're going to do perturbation theory. So as I explained yesterday, Weyl symmetry is crucial, and conformal symmetry is implied by it, and so that will restrict us to 10 dimensions. And in 10 dimensions, there are 5 different perturbative consistent supersymmetric string theories. Type 1 of open and closed, which includes orientable and non-orientable world sheets. And then type 2a and b, which are closed only and orientable, and heterotic, which are also closed only and orientable. And in the type 1 and type 2 theories, you also have D-branes, which I will not have the time to talk about. So today, I'm going to use the RNS formulation, which is probably the best understood in a logical way. And I'm going to restrict to closed orientable superstrings in 10 dimensions. So basically the four first ones out of 5. Okay, so now before giving you the formulation of the RNS string, I'm actually going to give you a few results without saying how they've been derived, just to start with some simple things, and then we'll get into more complicated things, because with the superstring things get complicated pretty fast. So the first result is very old, goes back to Green and Schwarz in '82, is the genus 0, so the tree level or sphere contribution to the 4-graviton amplitude. So I'm not sure in this audience it's necessary to remind you of the kinematics of the 4-graviton amplitude, but let me do it anyway. So we have some gravitons with momenta ki, and the momenta are conserved. We'll choose a basis of factorized polarization tensors. I think this is familiar from Svev's talk. Masslessness implies k squared equals 0, and transversality requires that each one of these polarization vector factors is transverse. So I introduce Mandelstam variables except for the fact that I make them massless. I make them, dimensionless. So I put in a factor of alpha prime with some funny normalization, which is very convenient. And then the usual ST and U are associated with the particular channels that you all know of. So here it is. The tree-level 4-graviton amplitude is given by the following expression. So GS is the coupling constant, string coupling, and it's tree-level, so it comes in to the power -2, as explained yesterday. Then there is a kinematical factor, which is also familiar to you from supergravity calculations in field theory, because it's the same factor. And it is factorized in terms of these factorized polarization tensors. Okay, so it's a product of k times k tilde. So I'm going to use epsilon and epsilon tilde here. And so one factor is given in terms of this gauge invariant combination of the polarization vector, which I'll call F. Call it F because it's like the field strength in electromagnetism, really. And so in terms of that, it's given like so, where the parentheses mean that the terms inside have been contracted cyclically with their Lorentz indices. So F12 is basically F1 mu nu times F2 nu mu, so that everybody is contracted. And then with 4, you have 4 of these guys circling around. So equivalently, you can express this in terms of this famous T8 tensor of Green and Schwarz, but this gives you a way of writing it down explicitly. So there's a similar factor k tilde by replacing epsilon by epsilon tilde. And this object is quartic in the polarization tensor. So in fact, it's proportional to a factor which we will call r to the 4th, where r is the linearized Weil tensor, is actually what comes in. Okay, you can think of it as a linearized Riemann tensor. Okay? And it's contracted in a peculiar way, which is given here, and this way is consistent with space-time supersymmetry. Then finally, there is this purely scalar kinematical factor, 1 over STU. So this has poles at STU, S and T and U being 0. So these correspond to massless exchange of gravitons. And then all this is the string stuff here. And so I've normalized things in such a way by my choice of S that this factor has poles at integers which are positive or 0. And so the massless poles essentially correspond to graviton exchange, but the higher masses correspond to genuine string, massive string exchanges. So this is the tree-level amplitude. So the 4 graviton one-loop amplitude was also written down by Green and Schwarz at that time. And so let me explain what it is, what it looks like. So it has the same kinematical factor as you had at tree level. So this is also familiar to you from supergravity, where the same thing happens in n=8 supergravity. And then we have an integral over the moduli space of genus 1, or of tori, which I explained yesterday to you. So it's the upper half plane quotiented by SL2Z. And here is the invariant volume form on the moduli space. It's invariant under SL2R, so in particular it's invariant under its SL2Z subgroup. And then there is an amplitude which I'll call it a partial amplitude, B, which is a scalar. It depends on the Mandelstam variables and on the modulus tau, and is given in a rather simple form. It's given by an integral over each of the 4 vertex insertion points of the gravitons, and then an exponential of a sum over the Mandelstam variables times the scalar Green's function on the torus. That's it. This is actually an extremely simple formula, and to derive it is, well, it's not that complicated depending on the way you do it, but nonetheless it's reasonably involved. I'm not going to give you the scalar Green's function for the moment. We'll discuss it this afternoon when we apply it. So for the heterotic, this is for type 2 A and B. For the heterotic string and for more external states at genus 1, there are similar formulas, which I will not write down. So since this is a meeting on amplitudes, clearly we want to ask what is the singularity structure in S, T, and U of these amplitudes. So first of all, if we fix tau, okay, then we can look at the singularities of B. Well, actually, the singularities of B are that of a free field theory on a torus. So you can analyze this rather easily. The Green's function has a standard singularity given by a log because we're in 2 dimensions. And when you integrate this combination, you will find that there are poles at positive integers Sij. This is just because the Green's function has a singularity as the points Zi and Zj come together. Okay. So the singularities of B are very simple. In fact, you can get them by looking at the operator product expansion of the vertex operators as the vertex operators come together.
Generically, there are no singularities except C0.
I'm sorry?
Generically, there are no singularities for general Sij.
For general S, for general STU?
Some variables.
What do you mean generically?
So if you have some variables, then an open set of this Mandelstam variables, there are no singularities.
Right. So it's only at the positive integers for each S, T, and U that you have a pole. The rest is analytic throughout the complex plane for each of them. However, you have to do the tau integral. So what happens with the tau integral? Actually, for large tau, the Green's function grows. So there are other singularities produced by that. And so if you look at this in detail, you can actually see that this integral is convergent only when the Sij are purely imaginary. This is not exactly in the real domain, but you can actually analytically continue to all S. And the only way I know how to do that is by decomposing moduli space and decomposing it in different pieces, analytically continuing in each piece, and then putting it all together. So the upshot is that you get branch cuts in Sij, starting at integers, but that includes 0. Okay. And the reason for the branch cuts is, of course, we have a one-loop amplitude. You can look at the discontinuity in any given channel, and you can have the exchange of 2 massless states. Okay. So that produces a branch cut. Or you can have the exchange of a massless and a massive state, in which case you get a branch cut, but starting at an integer not equal to 0. So that's the singularity structure. So I drew here the fundamental domain over which you integrate. So this is the entire upper half plane, and this is the coset of the quotient of the upper half plane by SL2Z, and it's just one choice. Of course, there's an infinite number of copies under SL2Z of this domain. Okay. Now, well, this is an amplitudes workshop, so you will ask, where are the loop momenta? Well, actually, you can introduce the loop momenta. They weren't present in the previous formula, but you can actually introduce them. Remember that on the torus I laid down yesterday some A and B cycles, some canonical homology basis. And so I can choose to define a loop momentum which flows through one of the cycles, let's say the A cycle. I'll show you later exactly how you do this. There is an operator that measures the momentum through a given cycle. And so you can impose that the flow through that cycle is a given number, p, actually a given vector, p. And so in fact, one can rewrite the amplitude of the previous page, the scalar part of it, as an integral over 10-dimensional loop momenta of an object, which is the integral over moduli, an integral over the points on the surface, and then effectively the absolute value of a locally holomorphic function. So locally holomorphic means that it's complex analytic, but it may have some cuts and some poles and so on and so forth. So I'll call this a chiral amplitude f, and so it depends on z and tau, but it doesn't depend on z bar and tau bar. That's what I mean by locally holomorphic. And in fact, you can write it down explicitly. So here it is. So there's some exponential stuff. And then there is a Jacobi theta function, which depends on the difference to the power of the kinematic variables. And then there is the integration volume form. Now, we take an absolute value here. And in fact, this is rather crucial because it turns out that this function f by itself is locally holomorphic, but it's not single valued on the torus. And so in particular, if I take one of the points, ZL, and move it around an A cycle, F picks up a phase. Well, that's no problem because we are actually dealing with the absolute value. So the absolute value is invariant, but the function itself is not. If I take a point Z and move it around the B cycle, then the effect of that is to shift the internal loop momentum by the external momentum associated with the point that you moved around the B cycle. Now this again, when substituted in here, you integrate over all the momenta with a translation invariant volume form. So the fact that you shifted one of the momenta is immaterial. So again, the entire amplitude is actually invariant. So now, of course, the A and B cycles, there is no God-given way of putting them down, so you can change them by making a modular transformation. And in fact, you can check that nothing really depends on the choices. You have an associated transformation of F. So what is P from remember yesterday we dealt a lot with conformal field theory. What is P from the point of view of conformal field theory? P actually labels the conformal block of the system. And so this idea of summing over all different conformal blocks and then pairing one chiral with its other chiral part is very familiar from conformal field theory. You have this Hermitian pairing between left and right blocks.
Do you consider P here as real or as complex?
Yes, I consider it as real.
It's real.
Yes. Yes, it has to be real. For example, this phase will be a phase only if P and K are real. Yes.
So if you do an ordinary field theory calculation, you might have a loop momentum, and then you might make a Schwinger or Feynman parameterization of it, and those would sort of correspond to tau and z.
Yes.
Now you have both loop momenta and the zi.
Right. That's right. Yes.
So it's not like you've, it's not a strict map to loop momentum in a field theory calculation in some sense, because you also have things that look like the Schwinger parameters in there too.
Yeah, but you have that in field theory too. You can have a diagram with an integration over internal loop momenta. And now I introduce Schwinger parameters, but I did not yet integrate out the loop momenta.
Haven't undone the
Right. So Jeff Fins, of course, Svi talked a lot about double copy, right? This, in a sense, is reminiscent of double copy because I put together left and right chiral parts. But the difference is that I still need to integrate over the positions of the vertex operators here. So it's something similar, but not quite the same. Now, let me immediately go to an application of this, which is UV finiteness. So actually, modular invariance is the reason that string theories are ultraviolet finite. This was shown for the closed bosonic string a very long time ago by Joel Shapiro, but it in fact holds for any modular invariant superstring theory to all genera. Since we have the genus 1 formula, let me just illustrate this for genus 1. Note that F, the internal loop momentum dependence of F was through this Gaussian factor, and then there's an exponential factor. All the rest is independent of P. So actually, every chiral amplitude of every superstring theory has this universal factor, this Gaussian factor. I wrote it down here for genus 1, but there is a general genus generalization of it, which is just as simple. And so, in fact, modular invariance allows you to choose an adapted fundamental domain where the imaginary part of tau, the plot here is for tau, the imaginary part of tau is actually bounded away uniformly from 0. Okay? So it starts here at something like the root of 3 over 2, but that's not very material. What's material is that the imaginary part of tau is bounded away from 0 in a uniform way. That means that this factor behaves as a Gaussian with a variance which is bounded from below, which is, okay. And that means that, in fact, you have a uniform suppression, Gaussian suppression at loop momenta which are large, which go to infinity. And that's actually the reason for UV finiteness. And you can make this argument for any loops. So the fundamental thing is that for string theory, the integration is over this region. If you did the analogous calculation in field theory, which I'm not going to explain, you would actually integrate over this domain going all the way down to the real axis. And this suppression argument will not work, obviously, because then you have no uniform suppression in tau, in P. Okay, well, I've postponed it long enough. Now we will have to come to the nits and grits of how this formulation works. So in the RNS formulation, we already had from yesterday the scalar fields on the world sheet that map the world sheet into space-time, X. So they're the same X's, except now they're going to run from 1 to 10. So in the RNS formulation, fermions are introduced by introducing spinors on the world sheet, but spinors which have a space-time Lorentz index. This is about the craziest thing you can think of, because you're after spinors in space-time. Okay. So the Green-Schwarz formulation would introduce at this point spinors in space-time that are scalars on the world sheet. This is almost exactly the opposite. Okay. So you'll have to bear with me, because for the moment this makes no sense. At least it should make no sense to you. So that means that psi mu has a Lorentz index. So the issue of negative norm states that we had yesterday for the X field and its time component also occurs here. Psi also will have a 10th component or 0th component that produces negative norm states. To counter that, we need a symmetry, and that symmetry is supersymmetry, local supersymmetry on the world sheet. And that will mean that the surface will be a super Riemann surface instead of an ordinary Riemann surface. So I'm going to explain all that. And the way you get fermions is there actually are two different kinds of ground states. An NS ground state, standing for Neveu-Schwarz, which is a boson of the Lorentz, is a tensor representation of the Lorentz group, and are fermions, which are spinor representations. Okay, so what is this field psi? Well, if you have Minkowski signature, where in 2 dimensions you can have 2 chiralities to a fermion, and in 2 dimensions they can be chosen to be Majorana-Weil, independent left and right chirality fermions. But if you have an Euclidean signature worldsheet, then psi, the 2 chiralities, are naturally Weil spinors in 2 dimensions, which are complex. Naturally, they're complex conjugates, but that's of one another. But that's not what you want for strength. You want a left and a right chirality fermion, which are independent Weil spinors. You can do this globally on a compact surface. Here the argument is sort of local. And then psi have to be sections of a spin bundle. And if we want Lorentz invariance, then in fact all the components of psi have to be sections of the same spin bundle. Spin bundles on a surface are labeled by their spin structures, which is essentially a plus-minus assignment for every homology cycle you can go around. And that produces 2 to the 2h different spin structures. And they have to be independent for left and right movers. So finally, I mentioned the GSO projection. This involves the summation over spin structures. And that summation, again, needs to occur independently for left and right chiralities. Okay, so that's sort of a flash of what I want to do. So now let me explain this a little bit. So first of all, what I want to illustrate is the difference between the Ramond and Neveu-Schwarz sectors, and then the independence of the chiralities. So let's take a spinor field of a given chirality, psi mu. We'll fix the complex structure on the worldsheet. We saw yesterday how to do that. And consider now the Dirac action for it, or Weil action if you wish. So the Dirac equation is just that, expressing the fact that psi is holomorphic. But when you have several fields, then you can have singularities, which are poles in the difference of the 2 location points. And so, in fact, you can show that each component of psi generates by itself a CFT with central charge 1/2. And we know from yesterday what that means. Okay. So now we want to quantize this gadget. And I'm going to quantize this on a flat cylinder. And by conformal transformation, you can map a cylinder onto an annulus. So if the coordinates of the cylinder are W, okay, then you can have this, you have this identification in the imaginary part, which gives you a cylinder. Or equivalently, if the annulus is centered at z is equal to 0, then you can obtain that by the exponential map, as I think you probably all know. So under this transformation, a 1 form transforms with an exponential, but if I have a spinor, I need a 1/2 form, and that transforms with the exponential to the 1/2. So you can see that as you go around the cycle where sigma goes to sigma plus 2 pi, for a spinor, you are actually allowed to pick up a sign because you're taking a square root of the transformation that accompanies a vector. So there are actually 2 different spin structures on a cylinder. You can write it either on the cylinder with a minus sign, and then when you move on to the annulus, that sign gets flipped here, becomes a plus. So on the annulus, you can have a field which is single valued as you turn around the point, or the opposite, on the cylinder plus sign and on the annulus a minus sign. So on the annulus, you would produce a branch cut. So these two possibilities are labeled Neveu-Schwarz and Ramond. When you quantize in operator formulation, you expand both of these fields in modes, and we choose the modes in such a way that the z factor gives you the dimension of a spinor, which is a half in 2 dimensions. And so you get, these are fermions, so they obey anti-commutation relations, which I wrote down here. So the moding of the Neveu-Schwarz sector is by half integers. The moding of the Ramond sector is by integers. So now we are interested in finding out how these gadgets transform under Lorentz transformations. Well, okay, then we need to construct the Lorentz generators. So here they are. This you just do by canonical Noether methods. So here the Lorentz generators in each sector. So in the Neveu-Schwarz sector, here it is. And in the Ramond sector, you have to be a little bit careful because there is a zero mode. There is the quantization in terms of integer moding includes the case where n is 0. Okay. And that's special because, well, it's self-conjugate under Hermitian conjugation. So here is JR. So here is the integer moded part, and then here is the zero mode part. So now yesterday we saw the Fock-based construction for the bosons. Well, let's do the Fock-based construction for the fermions. Let's start with the Neveu-Schwarz ground state. So it's defined by having all the B's annihilated when R is positive. There is no R equal to 0 in the Neveu-Schwarz sector. So this state is actually unique, and it's in the trivial representation of the Lorentz group. So you quantize it as a boson, it's a scalar. The Fock space is obtained by applying all the B's. Each B is a Lorentz vector, so when you reapply it, it becomes a tensor in general. So these are tensor representations, they're all space-time bosons. Now let's go on to the Ramond sector. So the Ramond sector you can define as having a state which is annihilated by all the positive modings. But of course you can't require that it also be annihilated by all the zero modes, because that's way too much. You have to split up the zero oscillators into a polarization, into half of them. Okay. If you wish, by analogy, this factor is similar to the Pauli matrices. When you have an orbital coupling, which would be the second part, and then you have an intrinsic spin coupling. Okay. So, in fact, the upshot of that is that the ground state is degenerate. And it transforms as a spinor. And so you have, in fact, a number of labels which label the spinor representation, which has dimension 32 in 10 dimensions. Okay? And that means that the ground state is a spinor, so whenever you apply the raising operators, you tensor with vector representations, it's always a spinor. So in fact, all the states in this sector are space-time fermions. Okay, so now summation over spin structures. Well, we have now a theory of bosons and fermions constructed from the Neveu-Schwarz and from the Ramond sectors. And so we want to include both. Nature has fermions and bosons. And so that means we're going to have to sum over spin structures, because the Neveu-Schwarz spin structure gave you bosons, the Ramond spin structure gave you fermions. You want both, so you need to sum over both. Okay. In the type 2 case, the spin structures of the two chiralities need to be independent of one another for the following reason. If I take the Ramond sector of the left times the Neveu-Schwarz sector of the right, that's going to give me fermions. Okay? Because one was a spinor and the other one was a tensor. The tensor product is again a spinor. If the spin structures of both were the same, that case would be excluded, because the spin structure on the left would have to be Ramond, then the spin structure on the right is Ramond too, but then I get a tensor representation. So in fact, the very fact that you want space-time fermions in the spectrum forces you in type 2 to have independent spin structures for both. I think I probably have emphasized this enough now at this point. Okay, so then now if you look at the torus, which is the cylinder where you identify both sides, there is a new spin structure pair that appears from that identification. And you also need to sum over that. That's actually a restriction of the GSO projection, where in the R sector you truncate to a chirality that's a definite chirality, one of the two. And in the Neveu-Schwarz sector, you eliminate a tachyon by doing this. So the upshot is that on a general Riemann surface, you will sum over all spin structures. Okay, now the second part of the construction of R and S is that the worldsheet is no longer just a Riemann surface, it's actually a super Riemann surface. So what does that mean? Well, we saw yesterday what an ordinary Riemann surface is. Locally, it's just like a piece of the complex planes, open sets mapped to open sets. So it's a complex manifold, which means that you cover it by patches, and then you have transition functions in between, and those are holomorphic functions. The complex structure is equal to the conformal structure here, and we discussed the moduli space. So what's a complex Riemann surface? Well, the first thing is a complex supermanifold, which is locally the complex plane, and when I put a slash and a 1 here, that means there is one bosonic dimension and one fermionic dimension to it. So in local coordinates, I have a coordinate z, but I also have a theta, a nilpotent complex coordinate theta. So I can define a complex supermanifold of dimension 1, 1 as one that has transition functions which map z theta into z prime theta prime, which are functions of z and theta. That would be the natural analog of what we did for a Riemann surface. But that's actually not the right thing for string theory. It generates an n equal 2 superconformal algebra, which is the wrong thing. So what one needs to do is something a little bit more sophisticated. You still have a surface that's locally C1, 1 with coordinates z theta, but you put a requirement that the transition functions rescale this odd coordinate derivative that you have seen, I think, when you studied supersymmetry. That gives you n equal 1 superconformal symmetry. So now you can ask, what is the moduli space of compact super Riemann surfaces? So basically we take the quotient of all these superconformal structures J by all possible reparametrizations that are consistent with this, and that gives you supermoduli space, the equivalence classes of superconformal structures, and I've given you here the dimensions. So for the sphere there is nobody, and for the torus it depends whether you have an even or odd spin structure. Not really going to explain what that means. And then for higher genus you have the familiar bosonic number of moduli, and you also have 2h minus 2 supermoduli, odd components. So for odd spin structure, by the way, even an odd, it means you count the number of zero modes of the Dirac operator, mod 2. That's what defines even and odd. So for odd, there is one odd modulus, but actually it's a bookkeeping device effectively. It's not, you know, it's fundamental, but it's very simple to handle. So the issue of odd moduli really arises first at genus 2. Okay, so let's see. I'm not sure how much of this I'm going to do, but let's get started. So I have insisted a lot on the fact that the left and the right parts of the of the superstring have to be independent of one another. And so that's actually what we're going to follow to construct the world sheets and the moduli spaces of the string theories we're interested in. So the most dramatic one is the heterotic string, where the left movers are like the bosonic string. So you take for the left movers a surface that's just an ordinary bosonic Riemann surface. And it is governed by a moduli space, which is just the ordinary bosonic moduli space. We can use coordinates for these things, z tilde and m tilde, for later use. So the right movers have the supersymmetry in it. So they will be governed by a super Riemann surface, sigma right, with its supermoduli space, and then associated coordinates. Now we have too many coordinates. We have too many dimensions, right? If we just take the product of these two, we'd have an independent z tilde and independent z. So actually what you need to do is you need to take a cycle in this product space where you identify z tilde complex conjugate with z, but you can't quite do that because you see z tilde is an ordinary bosonic coordinate, but z you're actually allowed to make super reparameterizations on. That would change what that is by theta dependent terms. So the best you can do is require that these two coincide up to nilpotent stuff. And so I denoted that here by taking the diagonal of the product of these two. And you do the same thing for the moduli space. Okay. And that in fact gives you the right dimensions of the world sheet and the right dimension of the world of the moduli space. So for type 2 it's analogous, but now both left and right are super Riemann surfaces. And again, you take their product and then you take a cycle of the right dimension in there. And you identify bosonic stuff, but you never identify fermionic stuff. They have to be independent of one another. So in each case I said you need to choose a cycle, but of course which choice of cycle is the right one? Well, actually Witten showed that this entire setup is consistent because one has a super Stokes type theorem which allows you to change the cycle provided all cycles obey these conditions. And so that gives you a consistent definition of superstring amplitudes to all genera. This was shown by Witten. Okay, so now a little bit more concretely, let me show you what the world sheet actions are, just as I did yesterday for the bosonic string. We now know what the world sheet is. It's a cycle in the product of left and right super Riemann surfaces. I'm going to do this for type 2. Each one has its independent superconformal structure with independent coordinates. So here is the world sheet matter field. So it has the X field, the psi field, the psi tilde field, and also there is an auxiliary field because we're doing supersymmetry. And so in local coordinates adapted to these super complex structures, I can write down this action rather simply. It's just actually the standard action for that I wrote down yesterday for X, and there's now a change for psi, which coincides with the Dirac action that I wrote down before. Now, of course, we're interested in integrating over all these super conformal structures. So having picked one is not particularly useful. We'll need to deform it. We'll need to change it and then integrate over all possible ones. So the way you do that is basically the changes in the metric yesterday we saw were governed by the stress tensor. So there is also here a stress tensor. And then analogously, there is a supercurrent component as well. So these two sets of fields for left movers and right movers is what will allow us to deform the complex structure. So I've written it down here, so you have some fields that multiply this, and Mu is a so-called Beltrami differential, and chi is a worldsheet gravitino. And so you can implement this and basically from one superconformal structure move around and deform it so that you can in the end integrate over it. Okay, well, Jeff DeVay didn't really give the derivation yesterday for the bosonic string in terms of ghosts. I'm not really going to go through that here either. Basically, by standard Fadeev-Popov procedure, you can now write down the integrand for the full amplitude, which is given like so. There are vertex operators, there are ghost and matter parts, and then there are insertions of ghost, of B ghosts, and an integration volume form for supermoduli space. So this this formulation is somewhat more general than the picture-changing operator formulation, and the picture-changing operator formulation may be obtained from this by a singular limit, which has problems, and some recently Sen and Witten actually proposed a slight variation of this, which eliminates those problems. Okay, so this amplitude is not quite yet what we want. Just as for the case of genus 1, one can introduce loop momenta. And here I wrote down the operator, so we choose canonical A and B cycles on the surface, and so we can introduce independent loop momenta by integrating this translation operator, dz of x, along A cycles, which do not intersect. You always have to define the loop momenta with respect to cycles that do not intersect. So once you do that, then in fact the previous amplitude can be rewritten as an integral over internal loop momenta, which are real, an integration over moduli in the positions of the vertex operators of a pairing, essentially a Hermitian pairing of left and right, where left depends holomorphically on the superconformal structures J tilde and Z tilde, and right have the opposite pair. So it's very similar to what I exhibited for genus 1, but now you have an integration over the full supermoduli space. So again, this is reminiscent of the double copy construction, except of course that you have the integrals over the moduli left over, the supermoduli. Okay, let's see. So what? I have about 10 minutes, is that right?
Yeah,
Okay.
13.
I'm sorry?
A little more.
13. Okay, very good. Okay, so now this is sort of the last part of the really hard stuff. Then hopefully, things relax a little bit after that. So how do we parameterize supermoduli? I haven't really told you how you parameterize moduli space, except for the torus. And that's a rather complicated business. But actually here, in a way, once you know how to parameterize moduli space, then the addition of these nilpotent variables, in a sense, should be fairly easy because they're nilpotent. So anytime I do some Taylor expansion, actually terminates after a finite number of terms. So that means there is, in fact, a systematic and beautiful way of constructing deformations of supercomplex structures in the following manner. In principle, you could change the transition functions you use on your super Riemann surface. In practice, that's horrendously complicated. So in practice, what you do is you turn on the gravitino fields on the worldsheet. And that gives you a local parameterization of supermoduli. So let me explain how that goes. Let's look first at how we parameterize moduli space locally. Well, you have a complex structure J, and you choose adapted complex coordinates, And in those coordinates, the metric is simply absolute value of dz squared. How can you deform the complex structure? Well, obviously you can deform the coordinates, but an alternative is you keep the same coordinates, but you deform the metric. Okay. So now the metric in those same coordinates is no longer of this diagonal form, but there is an offset. You mix dz and mu dz bar. Mu is this Beltrami differential. That's actually a systematic way of infinitesimally deforming the complex structure. And in fact, you can show that you can do this deformation not only infinitesimally, but actually finitely. You can integrate these up to a finite deformation. In field theory, this is actually very easy to realize because a deformation of the metric is governed by an insertion of the stress tensor. So you can actually show that a finite deformation of mu can be accounted for by the insertion of this operator in the exponential of the path integral with a finite value of mu. Well, that's good news because now it's almost straightforward to generalize this to supermoduli, because what we do is we start from a purely bosonic surface. I'm going to call this sigma reduced, purely bosonic, all the odd variables set to 0 with a certain complex structure. Okay. And now the way you deform, well, we know how to deform the complex structure. We insert mu t, but we also know how to deform the supercomplex structure. We just insert the gravitino field multiplied by the world sheet supercurrent. And that's actually the right thing. And these expressions are not just infinitesimal. They integrate up to the full thing. So I can actually go a finite distance in supermoduli space. All right. So far for the general theory. Now we would like some amplitudes of finite loop number. Right. So I told you that the first instance where the odd moduli come to haunt you is 2, genus 2 loops. So in the case of genus 2, an even spin structure, there is actually a holomorphic projection from supermoduli space to moduli space. By a projection, what I mean is you would like to get rid, you would like to integrate out all the odd stuff, right? Because you want an amplitude that you could put on a computer and actually compute. Perhaps people know how to put Grassmann numbers on a computer, but you would actually like a formula in the end for an amplitude as a complex number in terms of its complex data. So by integrating out is what I represent here by a projection. It's the same thing. You have a big space with odd variables. Now you integrate out only the odd variables and you end up on the even base. And so you need you can use a projection to do that. So we actually showed a number of years ago that there is such a projection for genus 2. But in more recent work, Donaghy and Witten showed that at least for 5 loops or more, and these 5 loops are not really related to the 5 loops that caused Zvi so much trouble. I mean, the number is 5, but not all 5s are equal. So for genus 5 or higher, there's actually no holomorphic projection. In between, somewhat uncertain, so I'm not mentioning it. Okay, so this is done with the help of the superperiod matrix. Let me explain what that gadget is. So when you have a canonical homology basis on a surface, you can introduce a dual space of holomorphic 1 forms, which I denoted by omega here. Okay, so these span the cohomology dual to this homology of 1 cycles. You can normalize them on A cycles. The A cycles are the ones on which we normalize the internal loop momenta. And then on the B cycles, they integrate to give you a matrix, and that matrix is the so-called period matrix. And for genus 1, it would just be 1 number, and that number is the modulus tau. So this is a generalization of that construction. Now on a super Riemann surface, you can essentially do the same thing, and you have corresponding super holomorphic forms, which also integrate to something, which is a superperiod matrix. And you can actually get explicit formulas for this. I'm not going to go too much in detail here. So here, the omegas I already explained. Chi is the worldsheet gravitino, and S is the Dirac propagator on the worldsheet. So, so in genus 2, every period matrix actually corresponds to an ordinary Riemann surface, and this allows you to associate with the super Riemann surface an ordinary bosonic variable omega, and that defines for you an ordinary Riemann surface. So that's the projection, actually. It's a way of getting rid of all the odd variables. Okay. All right, now we're almost there. So now how does this work in practice? Well, you take your chiral amplitudes. I defined them a couple of slides ago. I can now parameterize them by the bosonic variable of the superperiod matrix, and then the odd variables that I need to describe supermoduli. The chiral amplitude involves a measure and a correlation function. And so what you can do is basically you can integrate out in the odd directions and sum over all spin structures. You do this independently for left and right. And in the case of the heterotic string, the left is actually half of the bosonic string. And the full amplitude is then given by an integration over the loop momenta and over the moduli of an ordinary surface times the product of these two partial amplitudes. Okay, I know that that was a lot to absorb, but I wanted at least to give you, a picture of what's going on. And so now you can work this out concretely for genus 2. So what do we need for genus 2? Well, we need the analog of the upper half complex plane. Well, that's a known space. It's the Siegel upper half space. It's the space of 2 by 2 symmetric complex matrices which have a positive imaginary part. Yes, that's right. So the generalization of SL2Z, remember the modular group that was crucial in everything we did at genus 1, can be defined here as well. It's SP4. And the Siegel upper half space has a metric analogous to the Poincaré metric on the upper half space. And so for compact Riemann surfaces of genus 2, remember I defined the period matrix, and so the Riemann relations show you that the period matrix lives in this Siegel upper half space. And so there is a way of characterizing the moduli space at genus 2, which is just this Siegel upper half space divided by SP4Z. So it's known basically as well as for genus 1, with a little complication here and there. And so now I'm finally in a position to show you what the genus 2 4 graviton amplitudes are. So in the case of type 2, we have, well, this is 2 loops. It's genus 2. So the coupling constant now comes to the power plus 2, as opposed to 0 for 1 loop and minus 2 for tree level. We have the same kinematical factor. We have an integral over the genus 2 moduli space with this measure that I exhibited before, and then a partial amplitude, B, that I wrote down here. Okay. These formulas are very similar to genus 1, except for this measure of integration over the vertex operator points y, which I have given here. They depend on ST and U, and then on delta, which is this combination of holomorphic 1 forms. And G is the scalar Green's function on a genus 2 surface. Okay, so I'm just going to essentially leave it here, but this afternoon we will use this formula. Okay. So all this was to build up that formula. There's an analogous formula for the heterotic string, which is almost similar, but of course the bosonic part is a bit different, so it depends on which particles you're looking at. And that's more stuff that I don't want to discuss. So I'll stop here.
Thanks a lot, Eric. Time for some questions.
Yes?
Is there anything like a Pence decomposition for a superhuman surface?
Yes, I think there is. Basically, Fenchel-Nielsen, right? Fenchel-Nielsen is basically the Pant decomposition. Remember, in the very first transparency yesterday, I showed you that the fundamental interaction vertex is actually two disks going into one. That's called a pair of Pants in the mathematics literature. I'm not making this up. So you can actually cut every compact Riemann surface into Pants. Okay, the composition is not unique, but that's okay. And then Fenchel-Nielsen coordinates associate our coordinates for moduli, which are essentially the length of each boundary. And then when you put two of those together, there's an angle of gluing. Okay, that's Fenchel-Nielsen coordinates. So you do this, the length, you have to be measured in some metric, so they're measured in hyperbolic metric and constant negative curvature. And so that has a generalization to super Riemann surfaces too, because you can have a constant negative curvature manifold for them too. Actually, I think Albert has written, right? You used this at some point, I think, right? The OSP to 1 representation of super Riemann surfaces in the 80s. So I think there is some, there is something very close to what you want, if not exactly.
So this factor of k and k tilde that you have, I think that's equivalent to, or evaluates to STA tree, the symmetric factor that Zvi had in
ST,
so if you plug in helicity vectors.
but that's in 4 dimensions.
Right.
Right,
Just
okay.
saying, in that case, it evaluates to
Right.
Mandelstam variable S times T times the 4.3 amplitude.
Right.
That was a universal thing that Zvi had coming out. And it would be squared, of course, if you had the same
Right.
structure on both sides, like in the type 2 string.
Mm-hmm.
Do you know if that factor can be shown to hold to all loop orders?
No, I don't know.
So basically, you need to analyze each loop order separately, because sort of supersymmetry sort of suggests that
That's right.
that look like that, right?
That's right. So of course the RNS formulation, I didn't perhaps say it quite explicitly, but even though it has space-time supersymmetry, it's not manifest. Okay, so the Green-Schwarz formulation, it is manifest, but nobody knows how to quantize it to this order. And in the pure spinor formulation, supersymmetry is manifest. And in fact, I have it on my transparency somewhere, I think, that this formula for G of 2 was reproduced in the pure spinor formulation. So on the other hand, the pure spinor formulation doesn't really go to G of 3 for the moment. And RNS, well, my last transparency was in fact exactly about problems at G of 3. So also, there's no one has written down the amplitude for G of 3 at this point. So I don't know. I don't know of a general argument at this point.
Any other questions? Should we take a quick break before we go on? So let's thank Eric again.